Well, welcome to AP Chemistry and welcome to 2022, our first day back, but for me, not quite back. I think I have COVID, so I'm in the process of checking things out before I come back. And honestly, I don't feel up for it. Um, yeah, I hope you guys are well. You are missed, and I hope you had a happy new year and a great break and Merry Christmas and all that. Today, what we're going to do is we are going to watch this video, which, if you're watching, you are in the right place. And then you're going to work on the book work that goes associated with it. I'll show you where everything's at and what you can work on, and if you need help, where to find it. So today, our goal is that you understand what kinetics is, how to find average rate, how to find instantaneous rate, and how to use stoichiometry to figure out the rate of other stuff in equations. So this is chapter 14. Hopefully you have finished your outline for that, and hopefully finish the online quiz. I did check, and so far our average score is 88%, which I am down for that. So when we're talking about stuff in chemistry, kinetics is kind of its own thing. So there's like stoichiometry, there's all those other things, but kinetics is kind of its own beast. Kinetics is all about how fast things occur. So this is an important thing in chemistry because, like, let's say you make a pill like acetaminophen, and you want to know how long is it good for, or how long is it going to be active where it'll cure my headache. Well, you can do that with kinetics because it figures out how long stuff occurs, how fast things go. So kinetics, it basically, and I have a little writing tool, this answers the question, how fast? So when we're studying kinetics, we're looking at how the speed of things that go. So in chemistry, we often will refer to, let me get rid of that. We'll often refer to the rate. Okay, so this is the amount of change per unit of time. And so if we're talking about speed, we'd be talking about miles per hour or meters per second. But in chemistry, when we're talking about the change in concentration. So concentration is molarity. Remember, that's moles per liter. And then seconds is usually what we measured in. It can be seconds, hours, years. It doesn't matter, some unit of time. So usually we're looking at the change in concentration, okay, molarity, always molarity, moles per liter, over the change in some time. Now, when you're doing kinetics, the AP College Board, they're unit obsessed. So what I mean by that is they really care about the units. So sometimes you're going to see it as big M per minute or big M per year, or they might try to get fancy, moles, liters to the negative first, seconds to the negative first, which is all the same thing as this. But regardless, it's the rate of change of reactant or product that changes over a unit of time. So usually you're going to be given some sort of data table or something, and you're going to have to figure out how does this slow down, or how does this speed up, or all that kind of stuff. So that being said, let's go on to the next thing, which is what makes things go faster. Okay, so a couple things will affect the rate of, how much a reaction occurs or how fast it occurs. First of all, the state of reactants matters. It matters a lot. So if we're talking about two solids reacting, like, it could take forever. Okay, whereas two gases, they mix right away. Usually those are the fastest. So it kind of goes like this. When we're talking about speed of reactions, gas goes first, liquid goes second, then solid is usually the slowest. Now, if it is a solid, surface area is important. Surface area is like how big the size of the material is. So like powdered tends to react faster than, chunks of it. Concentration of reactants matters. Sometimes during chem lab, and they're going to ask you all these things all the time, conceptual stuff. They like this. So like, if something's going too slow, I was like, add more acid, right? Well, if you up the concentration, you're going to get more collisions, and the rate, or how fast it's going to go, is going to go. Okay. And then typically temperature is something that makes it go faster too. So if you have more effective collisions, or more collisions and they're faster, then you're going to go, the reaction is going to be faster or slower if it's colder. And then finally, there's going to be something we're going to talk about. It's called catalyst. And we've used these like when we did H2O2, we made some oxygen earlier. We put the catalyst on the arrow, and this is breaking law, so don't try to get me on that. Plus, I'm not even there to pay back. Okay, so regardless, this doesn't get used up. It just allows the molecules to react faster. It orients them in a certain way. And in AP Bio, if you took that last year, you talked about enzymes, and that's kind of the concept of bio catalysts there. So, anyways, when we're talking about kinetics, we're talking about how things can go faster, and you have to know all this kind of conceptual stuff when we're talking about that. Okay, let's keep going on. All right. Now, when we measure rates, okay, we always take the change in concentration over the change in time. Okay. And that's where I was just saying that they'll often refer to it as the rate is equal to delta and then some variable over delta T, where this is the brackets mean concentration, molarity, and then this is all down here. And then change in time is the change in time that takes place in something. So if we're disappearing, we say it's negative, okay? And if we're appearing or it's a product, we will make it positive. So that's what we do when we do kinetics. Okay, let me trash that. Okay, so I might be like, all right, hey, let's find the rate of, change or rate of reaction in the first 50 seconds. So if we were to do this, you would take, all right, here's the change in, let me mark this up here. So you would take the change in these two right here, see 0.1 minus 0.095 divided by the change in time. And then this is the change in disappearance or average rate. And you can see that as you go, like this is very common. You'll have like data time, and you can see the rate slows down as the reaction proceeds. And the reason it slows down is like the concentration goes down. There's less of it. And so reactions always tend to kind of look like this as they react. They slow down towards the end. So you can see that the initial rate is much faster than the final rate. And you can do the rate over different times. Okay. So first off, this is called the average rate. It's looking at the speed at various points in the reaction. And, if you're driving to Florida, your average rate could be the total distance over the total time. You could look at the total time and then, the total concentration change, and that's your average rate. That's kind of how it's done. Or we can find something called the instantaneous rate, which is what we're going to look at next. And to do that, what you have to do is you have to draw a tangent line. Now, this is weird. And this is what you do is usually you're given this, but if you're not given it, you have to draw it yourself. If you want to find the rate at some point, we'll call it T equals 600 seconds right here. Okay. You have to, and I'm going to try to get this really close. All right. You're going to have to draw a tangent line right that just touches at that point. And then you find the slope of that line. Well, slope is rise over run. So this is the rise and this is the run. And it doesn't matter how big you make the line, it's still the slope, the change in y over the change in x. And that is the speed at that moment. I have one coming up here. Let me show you. Okay, let me get rid of that. Okay, so here we go. All right, so when we do change of rate, it typically decreases over time because I said this, like the concentration changes over time. They always tend to slow down. But the instantaneous rate, that's the difference thing that we're talking about. That's where you actually have to draw a tangent line, which is something like this. And then you have to like find the slope of it at that point. So, you can draw a tangent line right here at t equals 0. And that's how you do that one. Or you can draw it right here, or you could find it right here. You draw a tangent line and go from there. So there's two ways to find rate. There's average rate, which is the change over time. And if we're doing that, I'm going to go back up here. If we're doing that, that's where can I go? Will it let me? Okay, that's where you take the data table and you take the difference between the two. And if they ask for instantaneous rate, that's when they usually have to draw the slope of the line and figure it out from that. Now, usually they don't make you do this on AP too often, or they'll give it to you like this and you have to find it. So they don't usually make it, but on the homework you have to do this. So when they say instantaneous rate, that's what they're referring to. Okay, let's keep going. All right, now here's a couple things with this. Now this is just a data set, which is very typical of what you would have to do in kinetics. So you can see that over time, the concentration changes. And so if I was to ask you, okay, what is the average rate for the first 10.5 seconds, you would just, you would just literally like take the change in concentration, these two. So 0.0045 minus 0.005. That's the difference between those over, 0 minus or 10.5 minus 0, right? And then you just, that's what you do. You just take the difference over. You just like that. But if I'm doing the instantaneous time, that's when let's say I needed it at exactly this point right here. This is when you draw that tangent line and find the slope of the tangent line. Tangent line is just a line that touches right at the point you're looking at. Okay. So most people, when I looked at what they've done, they've not had issues with finding the rate. Rate is just the concentration, the M over the T, the change in M over the change in T. And you can do that at any point here. People don't like the instantaneous rate thing because it's annoying. Okay, first of all, it's annoying because you have to draw an extra line in there. It's annoying because you then have to find the slope of it, but that's what you do. It's just like so much of chem, right? Okay, so this is just an example. This is showing you, this is the actual answer if I were to do the average rate between these two. And it's, notice the units are molarity per second because the change in molarity over the change in time. And, I already showed you that in the previous, but that would be the answer to the previous one that I was showing you. So, what is the average rate? So that would be 0.05 minus 0.045 and then over the time difference. And that's what you get. And now, if I was to do the instantaneous rate at said time, so this is the same one, and they're saying, okay, now you need it at exactly 100 seconds, and here's 100 seconds. So I draw my tangent line that touches just right at the 100. Now, does everyone draw all the same tangent line when they do this? No. In fact, some kids are a little bit off, but you get a good estimate, and that's kind of what this is about. And then you take the rise. Okay, so this is our rise over run. So you can see these are the change in y over the change in x. And that will give you the instantaneous rate at said time. Okay, so you have to do two things, right? And we'll see if I can do this. Two things. Find the average rate, which is from the data table, or find the instantaneous rate, which is from a tangent line. Okay, it's so easy. Right? Right. So easy. Okay, so everything's kind of related. So the rate of disappearance is often equal to the rate of appearance and that kind of stuff. And so we say that this is a typical reaction right here. So this is like my reactants, and these are disappearing. Notice that they have negative rates. And then these are appearing, so they have positive rates. So the relationship between them, if I have something like, I don't know, if there's like a 1 here and then a 2 here, well, it just so happens that this is going to appear at twice the rate that that's going to disappear. So this sets everything up in such a way where if you use this formula, it shows you how each reactant is related to each other. And likewise, if I have a 4 here, this is going to disappear at a rate 4 times that of this. So like the rates of these things, we would say, let me just throw these numbers in. So I have 1, 4, 2, and then we'll just do a 3. So the rate is equal to negative, or it'd be negative 1 over 1. So we'll just, whatever. And the change of A over the change in time, okay, which is equal to negative 1/4, right, of the change in B over the change in T. And this is really sloppy. I'm sorry, it's hard to write. But regardless, we can still see conceptually that this is going to disappear at 4 times the rate that this is going to disappear. And this will appear twice the rate as 1, but half the rate of 4. And this is all just a way to show you how everything is proportional. So it's like stoichiometry matters in kinetics, and it affects the rates of it. Let's see what it looks like problem-wise. Let me get rid of this and go here. All right, so here's a really good example of what it all looks like. So if we're talking about the rate of disappearance of, HI, that would be hydroiodic acid. This is strong acid. And then I have H2 and I2. And they're saying, all right, well, how do the other things, like what's the rate of HI if this stuff right here is forming at a rate that's 1.8 times 10 to the negative 6 moles per liter per second? So what we know is that this guy right here is going to disappear at twice the rate of that guy. And really you can tell that because you can see that this rate, which we'll just call 1.8 right now, just because it is. All right, we'll get rid of this thing. And you can see that this would be half. If this is the rate, half of this would be equal to that. So we automatically can, if we're solving for this, we can figure out that it's exactly 3.6 times 10 to the negative 6 molarity, moles per liter per second, would be the rate of the other one, because the coefficients tell us how each is related. And that's really what you have to know. Okay, so when expressing it, you use the, 1/2 or whatever the coefficient is. That's this thing. Let me clear this. That's these coefficients right here. Okay, and that is how everything's kind of related to each other. Okay, now let me show you where everything's at. So I've been kind of working on this as much as I can. So I'm going to add this video in here after this is done. This is the assignment sheet. So these are tutorials and videos of stuff. So this is actually really good. I kind of put this together before we left. So let me go here. And, this is like factors affecting rate, initial rates, not that yet. So pretty much this first video would be something that you could supplement on this if you need extra help. Okay, so this is extra tutorials. Let me go back here. Now, rather than, I had something else, but I'm just going to make it simple. So you all download this. And this is all the assignments that we're going to be working on. And I don't know how long I'm going to be virtual here. I'm technically okay to go back, but I can't go back. I can't stay up like standing very long. So it's been rough. So anyways, we're going to make it simple. You guys read through this first section, which you probably already done. And then you're going to work on page 3 or 610, 3, 17, 18, 19, 22, 23, 25. Now, you need to graph this, okay? I'm not going to accept, and you can all work on this. Like, as soon as you're done with this, you can work on this. But you're going to go here, which is, it's going to sign me out. Shoot. It's been a while. Oh, okay. So it's still loaded up. It must be still signed in. So these are the questions in your online textbook. It's in chapter 14. And let me show you what you're doing. So, what are the units usually expressed to describe rates of reaction? That's molarity per second, molarity per minute. This is all conceptual stuff, right? Then comes the math. Okay, could you find the rate if you're looking at moles, right, and the change in time? Heck yeah, you can. You just do molarity over time. But the one I'm worried about, oh my gosh, is this one, number 22. Okay, so this one, you need to graph it. Okay. So when you do this one, because you're going to have to find the exact time, the tangent line thing. So you're going to want to graph this, and you should probably use graph paper. So I'm going to try to make sure the sub has graph paper for you to do the assignment. So anywhere it says graph, use graph paper. Okay. We're all going to hang in there. We're going to get through this. 2022 is going to be better. It's going to. I say that and I'm like, but we've got this, people. All right. So hang in there and we will talk to you hopefully Tuesday. I can come in. Okay. Bye.